So now we're going to talk about torsion. First we're going to talk about strain, and then we're going to talk about stress, and then we're going to talk about like ways to calculate it and stuff. Oh yeah, also angle of twist. So starting with strain, if you remember strain, it's basically when I apply a load that creates an internal stress. In this case, we're going to have a shear stress, and then that stress is going to cause an amount of deformation. In this case, the deformation is going to be angular right here. So basically, if I have this circular shaft right here, in this video, we're only going to be looking at circular cases because we're going to need to have the radius. Like the radius is a pretty important value. You can see right here, rho in the derivation. And a lot of times we do have these kind of long circular objects. So you can see right here that we have our L, that's our length. C is basically the maximum radius, and then rho will just be some general radius. This longitudinal axis right here we're calling X, and then we have A, which is the fixed endpoint, and B, which is this endpoint right here. Then we go ahead and we can apply a torque on the end, and then this is going to cause basically it to shift. You see right here we have these straight lines, and then everything twists a little bit. So this angle of twist, we call it phi. And if we look a little slice of this delta x right here, if I come down here, you can see this right here is our slice delta x. We have a radius rho that we're examining. This dotted line is kind of the outer radius c. So you can see right here, this is our angle that we've deformed by phi. And then this angle right here will tell us about our shear stress, because if you think about it, basically if you remember our shear stress, so if I have like a rectangle right here and I shear it like this, the shear strain is going to be the amount that it basically deforms in this direction. So this delta divided by the length right here, we'll just call this like L or something. So you can see that our L, I guess this would actually be our delta in this case. So if this is our corresponding delta, and then this length right here would be our corresponding L. So our shear strain, gamma, would be equal to this length right here, delta, over, and then our length is just delta x right here, right? Now, if you remember from the definition of radians, we're going to be assuming we're using radians right here. If I have a circle, and basically it has some radius r, and I go across some length theta, so I guess the length is actually s, and the angle right here is theta, then if we're using radians, then we know that s is equal to theta times r, which means that our length delta right here is going to be our radius rho times this delta phi. So we can say this is equal to rho delta phi, where our delta phi is the change in angle of twist as we go along some slice delta x, all divided by delta x. And now if we take the limit as delta x approaches 0, this is going to give us the shear strain, the torsional shear strain at a specific point. So we can say that gamma, so this would be the average then, but gamma at a point is going to be equal to rho, whatever radius we're looking at, because the shear strain will be different at different radii, times d phi dx, so the amount that it twists per unit step delta x. And then we can go ahead and also say real quick that our max shear strain is just going to be at our maximum radius, right? Because the higher radius, this phi right here, is going to be larger. So our maximum radius, we said, is equal to c times d phi over dx. And then that also means that our gamma at some radius rho is going to equal basically rho over c times gamma max, right? Because if we multiply this term by rho over c, then we would just get our shear strain at some radius rho. Now for the torsional shear stress, what we're going to do is we already assumed that it's circular, right? So we're looking at rho right here, but we're also going to assume that we're within the elastic region. So if you remember when we were talking about loading and shear, so this is our stress strain diagram. Basically, there's a region where they're linear before we get yielding, and then it does like fracture or something, and this is like the end of it. It would be kind of like this because this is where we're necking. But anyway, we're assuming we're in this region right here, which means that stress and strain have a linear relationship, and for shear, that's G. So our shear stress, tau, is equal to G times our shear strain, gamma. So we can also go ahead and say that our maximum or our outer shear stress, so we can say this is like tau max, is going to be equal to G times gamma max, or I guess this would be at some radius rho, so we can call this rho and rho right here. And now if we substitute this into this equation up here, what we're going to get is that shear at some radius rho divided by G, because that's when we're solving for our gamma rho, is equal to gamma max, which would be our shear max over G, times this rho over C term. So we'll have a tau max over G, and now we can multiply across the G's. And so this implies that our shear at some radius rho is equal to rho over C times shear max, which means that if we can just find the shear at some radius rho, then we're going to be able to relate that to the max shear. So now if we go ahead and we take a look at this cross section on the right, we're going to be able to figure out what our shear stress is going to be. So basically this is like a slice, a circular slice, right, where we have some differential slice of area dA at some radius rho, and that's going to have a force dF, which is equal to our shear at that rho times dA. And then if we multiply dF by rho, we get the torque. Now real quick, just to make sure you understand what's going on, if we were to look at this and we had like a circular slice like this, right, the stress, the shear stress of some element is basically going to be, like if I had a torque in this direction, then we would expect it to have a shear stress this way, and that would also imply this way and this way, right? But remember that this is really just a shorthand for a 3D element. So if I can draw a 3D stress element, where this shear right here is on this area right here, like this. And so this area is the cross-sectional area that we're looking at right here. So when we say shear dA, this is the shear we're looking at, and this right here is the dA when we look at the cross-section. So now if we add up all of the differential area times rho times tau, so we have dF times rho, that has to equal our torque, right? So we can say that T has to equal the integral of our differential T, which has to be the integral of our radius, times our force, which is tau dA across our whole cross-sectional area right here. And now if we substitute in tau rho with this equation we have right here, we're going to get that this is equal to the integral over our area of rho times rho tau max over C dA. Now our tau max is a constant with respect to, any slice of dA on here, and our C, which is the maximum radius, is also a constant. So if we go ahead and we pull those out of here, what we'll have is that this right here is equal to tau max over C integral of rho squared dA. And this integral right here, we're going to call it J. It's called the polar moment of inertia. So this means that this is equal to tau max times J over C. Or if we rearrange, because remember this is equal to T right here, then we can say that, kind of ran out of room here, tau max is equal to T, the applied torque, times C over J. And this right here, this is going to be an equation you're going to want to box in or remember something, because it's going to be used quite a lot. And real quick, because of our ratio of our maximum and our rho, if you plug that in, that would also mean that the tau just at some general radius, so if it's just over here, the tau at some general radius is equal to T times whatever radius that happens to be over J. So now we're going to talk about angle of twist. And just real quick, this is the sign convention for like torque and angle of twist and all of that. So you can see basically our T is pointing away, like in tension, like the sign convention for our normal. What that means is that our torque is going to wrap around it in the direction that you would find with the right hand rule, right? So if my thumb was pointing out in this direction, this is a little bit hard to show you because I can't really show you what my hand is doing, but basically your fingers would curl in this direction right here. I know that's a pretty bad drawing, but I hope you get the idea. And then for this way, you'd have your thumb pointing this way, and then your fingers would kind of curl in this direction like that, which is where we get the torque in this direction from. And then for P's, which are our angles of twist, it's going to be the same thing. This is the positive direction, and this right here is the positive direction on this side. So what we're going to do is we're going to start with what we already found. So we found that tau at some radius rho equals T times rho over J. And we also, if you recall, our shear strain is equal to rho times d phi over dx. And then lastly, we're going to use this elastic equation. This is technically a variation of Hooke's law, by the way. Our shear stress at some radius rho is equal to G times our shear strain. And now we're going to plug this all in together. So we have that this right here, we'll put here, so we have T rho over j equals g rho d phi dx. And now what we're going to do is we're going to basically divide over this g and this rho, which are going to cancel because of rho on each side. And then we're going to do a little bit of a funky thing that's technically not super formal, where we're going to multiply over the dx and put integrals on both sides. So this is going to be d phi is equal to t over jg dx, and we throw an integral on each side. And if you don't like that, a way you can think about this is basically I'm going to integrate both sides with respect to x, but on the side that has the d phi, I would basically get a d phi dx integrated dx, and so by the chain rule, these would cancel, and it would just give us the same thing that we have here. Now this means that our delta phi is going to equal t times the length. I guess this is integrated across the length. I should have made that more clear because we're integrating dx, right, which is in this direction, across the entire length that we're interested in to get the angle of twist, which is the delta phi between two locations, right? And because all of these are constants with respect to x, then it's just going to add an L term right here. So anyway, this is going to be TL over JG. And again, this is something you're going to want to box in or something. And our T, technically it might not be constant. If you can imagine, we might have different sections where we're applying different torques. And in that case, all you have to do is add up the angle of twist in each of the locations. So if I had like some tube right here, and then another section of the tube, and I have like a torque this way and a torque this way, then what I would do is I would find the torque in this section right here with a cut. If you remember, basically I can like cut this and then sum the torques along this axis, which would give me the internal torque in this section right here. And then I would also find the internal torque in this section right here. And then my total angle of twist, phi, would be equal to the sum of my TL over JGs for each of the sections. So let's go ahead and take a look at an example right here. I know I kind of gave some numbers for some of these, but then I realized it'd probably be better to do these in terms of just variables, because I'm assuming by now you know how to plug in numbers into the variables, right? So it's probably better to just understand conceptually how we're manipulating each of the variables. So we can see we have two sections right here, and we want to find the angle of twist. So we know that there's going to be no twist right here because we have a fixed connection on this side, which means that basically we can add the angle of twist in this section and the angle of twist in this section because they're going to have constant torques. And if we combine those, we'll get the total angle of twist of this thing. So let's go ahead and start with D1. Why not? So you see we have one section right here, and then we have a torque, T1, and we have another section, and then we have a torque in the opposite direction, T2. And we know that some internal torque in this section somewhere, which we're going to have here, this is going to be basically our positive sign convention. If you imagine we cut this and we have like a section right here, we would have tension this way, which means that we would have torque in this direction. So we're going to assume by our sign convention that the torque applied is in this direction right here. And we'll just call this T. We should not call that T1. We'll call it T I1 for like T internal 1 or something, right? And now what I would do is I would sum all of my torques along the x-axis. This has to equal 0. So this would give me, well, in the positive direction, I have T1, and then I have a minus T2, minus Ti1, and then I could use this if I'm given T1 and T2 to solve for my Ti1, right? I would get that Ti1 is equal to T1 minus T2. All right, now remember what I need for angle of twist. I need T, L, J, G. They give me L right here, it's L1. G is also given, so the last thing I need is J, right? Now J, if you remember, is equal to the integral of rho squared dA across our entire area. Sorry, I was a little bit scrolled off to the side there. So if we think about a circle, right, and we're integrating, it'd probably be best to do polar coordinates here. So we're going to have our polar axis, and then it'll be some angle theta, and then this will be our r axis right here, and we're going to be integrating across the entire area. So we're going to have an integral from r equals 0 to our outer radius, or I guess rho equals 0, and theta equals 0 to 2 pi of rho squared, and if you remember, we need an r dr, which I guess we'll just make this rho d theta. Now this inner integral right here is going to give us, well, we'll have rho to the third, so we're going to add 1, that'll give us rho to the fourth, and we'll have a 1/4 outside that. This will be integral of 1/4 r to the fourth d theta, which is equal to 2 pi over 4 r to the fourth, which is equal to pi over 2 r to the fourth. We're going to put a c here because r is our outer radius. This is equal to pi over 2 c to the fourth. Or, if we want to, we can pull out a 2 to the fourth, which is 2, 4, 8, 16. So we can say that this is equal to pi over 32 times our diameter to the fourth as well. And so now we can go ahead and give the whole angle of twist for section 1. It's equal to TL over JG, which we just found. This is equal to T1 minus T2. So we can say phi section 1 is equal to T1 minus T2, that's our internal torque, times L, which is L1 that's given, over, now our J is equal to pi over 32 times our diameter is given, so we'll put this as D1 to the fourth. Make sure you put to the fourth here in your calculator. I made this squared all the time, and it does, in fact, not give you the right answer. And then lastly, we'll have a G right here, right? And then and then we'd also need to find our phi for section 2, but notice we've already found our equation for J. We have G, we have L. The only thing that we're going to need is our internal torque. So if we go ahead and we think about this, it's a pretty simple free body diagram. We would just have some section right here on the outside, right? And we would have this applied torque right here like this. Our internal torque, if we think about this direction, would have a sign convention of this way. So this is T2. Therefore, we can say that the internal torque of section 2 is equal to negative T2, which means that phi 2 is equal to negative T2 L2 over pi over 32 times D2 to the fourth times G, which is the property for this material. Technically, we could have a different G for section 1 and section 2 if they're made of different materials, like if one was steel and one was aluminum or something. And then, if we want our angle of twist, delta phi, all we have to do is add phi 1 and phi 2. There might have been some weird cropping stuff right here, so just to make sure you have the right equation, up here we have phi 1, T1 minus T2, L1 over all of this. It's the same as our phi 2 except for our internal torque, and then we just add them. And then on this side right here, this is the free body diagram. Basically, we just have a T2 applied at the end, and then our internal torque then has to be negative T2. Now real quick, just some things to keep in mind that can help you when you're solving problems are the idea of superposition and end conditions. So if you look at these examples right here, we get a pretty good example for when each of these would be useful. So right here you can see that we have a shaft right here. It's got like a motor or something right here fixed at this end, and then we have torques applied at each of these positions right here. And basically the principle of superposition says that we can get the angle of twist for this entire shaft and this entire loading by adding the angles of twist as if the shaft only had one of these. So basically what we could do is we could say, let's look at the shaft that only has this T1 right here, right? And this is going to give me some phi. We'll call this like phi 1, where phi 1 would be my angle of twist of the entire beam or the entire shaft under this singular loading, right? And then I would take another one and I would look at just the case where we have T2, and then I would get my phi 2, right? And then I would do the same thing where I would look at just the case where I have T3 applied, and this would give me phi 3, and then I would add phi 1, phi 2, and phi 3 because they add constructively, and that would get me the total angle of twist. And then end conditions are a way that we can force our equations basically to kind of give us more information to solve the problem. So you can see right here is an example. This right here is a center line. It means that this is basically symmetric about this center. You can see because it has a long and then a short and a long and a short, and it's a dashed line. So basically this right here is like a solid cylinder, and then we have a hollow cylinder, and it's fixed at both ends right here. We have an applied torque T. So thinking about this right here, because this whole thing has to be in static equilibrium, if I have like some section right here and it's got a hole in the middle and this hole extends through right here, then I can say that my applied torque T has to balance with whatever torque comes on it, the internal torque on this side of it. So we'll just call this like, I don't know, TBC, with this torque AB will also be here as well. So TAB plus, or I guess maybe not plus is correct. So this would be a torque, remember, so it's going to look like a turning direction. Anyway, so if I add all the torques along, let's just call this like my x-axis, I would say that T minus TAB plus TBC, this is actually in the wrong direction because I messed up my right hand rule. If I add all of these along the x-axis, then I know that they have to be equal. Some other things I know are that, well, this is given from the problem statement, which I didn't really write out. They're saying that we're going to apply the torque until the angle of twist at this location is at max 5 degrees, which means that I would know that if you think about this, basically what's going to happen is this end's going to have no rotation, this end's going to have no rotation. It's going to start here, it's going to rotate some, and then it's basically going to wind back like this, right? So I can say that my angle of twist in section AB has to be equal and opposite to my angle of twist in section BC. So basically knowing what is fixed and what isn't allows you to create end conditions or equations like angles of twist that can help you solve problems involving torsional stress.